Today we continue our discussion on 0-1 problems. We try to look at a few things. We said that our standard problem is a minimization problem. With all constraints of the greater than or equal to type, and of course all variables are 0 and 1. More importantly, the minimization objective function is such that the objective function coefficients are all non-negative. So, if we have a less than or equal to constraint, then we multiply the constraint with a -1 and convert it to a greater than or equal to, which is a known way of doing it, and we do not have to unduly worry about the right hand side values. The standard problem does not assume that the right hand side values are non-negative. Right hand side values can still be negative, so that does not matter. So, step 1 is, if you have a less than or equal to inequality, multiply with a -1 to get a greater than or equal to inequality here. If you have a maximization objective, once again multiply the objective function with a -1 to make it a minimization problem. So, these two things are possible. Now, how do we ensure that every term in the objective function has a non-negative coefficient? If there is a variable x j with a negative coefficient in the objective function, replace it with an x j dash equal to 1 minus x j, so that it effectively takes a non-negative coefficient, in this case a positive coefficient, and because x j is a 0-1 variable, x j dash is 1 minus x j dash is also a 0-1 variable. So, this way we will be able to convert every given problem into the standard form. Standard form is the form where you have a minimization objective function, all constraints of the greater than or equal to type, and all variables in the objective function having a non-negative value. There can be a constant. As a result of this conversion, we might have at the end a plus or minus constant, and that constant is all right. You can always take a constant out of the objective function, solve it, and then add or subtract that constant depending on what the sign of the constant is. The only thing that we have not looked at is what happens when I have an equation. The variable definition is only one way, which is a 0-1. So, we do not worry about initialization with respect to the nature of the variables. We are only worried about initialization with respect to nature of the constraints and the objective function. So, objective function we have seen, constraints we have seen, except the equation. Suppose we have an equation which is like this. Suppose we have an equation x1 plus 2x2 minus x3 equal to 6, say. Now, what we do is we write x1 equal to 6 minus 2x2 plus x3. It's all right. I was just giving you a value. So, maybe if you do not like the 6, you could keep it as 1. So, say you have 1 minus 2x2 plus x3, and then this x1 being a 0 or 1 would simply give you two constraints with an either or relationship. So, this would give you x1 is either, now this is written as when x1 is 0, okay, this becomes, when x1 is 0, this becomes 2x2 minus x3 equal to 1. When x1 is 1, it becomes 2x2 minus x3 equal to 0. Okay, that is what happens here when you do this. Let me see what I. sorry. So, what we do is this is x1 equal to this, x1 being a 0 1 variable is now written as x1 greater than or equal to 0, x1 less than or equal to 1, x1 defined as a 0 1 variable. Now, x1 greater than or equal to 0 would give you 1 minus 2 x2 plus x3 greater than or equal to 0. So, 2 x2 plus x3 less than or equal to 1, and 1 minus 2 x2 plus x3 less than or equal to 1 would give us minus 2 x2 plus x3 less than or equal to 0. Two x2 minus x3 less than or equal to 1 minus 2 x2 plus x3 less than or equal to 0. So, every equation now becomes 2 constraints. So, we end up adding one more constraint for every equation. The variable retains, but we have eliminated one variable from the analysis. X1 it does not exist anymore. So, typically if you have to solve a 0 1 problem with many equations, you would get into this kind of a situation. Now, if we have say 5 equations, then we end up writing 5 constraints for the greater than or equal to, 5 constraints for the less than or equal to. For the less than or equal to 1 and greater than or equal to 0, one of them you can simply add, particularly the less than or equal to type constraints you can add and convert 5 of them into a single constraint depending on the problem. But as a general rule, if you have an equation, then you end up creating 2 constraints for you eliminate the equation and you eliminate one variable from the equation, but then you have to create one additional constraint. So, there will be 2 constraints. So, to that extent the problem becomes little more involved and cumbersome whenever you are having equations, because the time taken obviously depends on the number of constraints, and with equations the number of constraints increases considerably. The last part that we have to see in this is what happens when we have variables of this form. Suppose I have this, minimize z equal to x23 plus x2 plus x3, or we to generalize it we put some x2 square plus x3 cubed, where all x are 0 1 variables. So, we know that this x2 square and x3 cube will become simply x2 and x3 because of the 0 1 nature of the variables. The only thing we need to do is to model this x2 x3. I will just write down the equations for you. Yes, you can take any variable, you can choose it. It is not necessary that you should eliminate only x1, you could eliminate x2 or x3. The equations will change accordingly. So, you will have y, you will replace x2 x3 by y and then say that x2 plus x3 minus y1 less than or equal to 1 minus x2 minus x3 plus 2y1 less than or equal to 0, x2 x3 y1 equal to 0 1. So, x2 x3 will be replaced by y1 and then you will have this. So, for every product term you will have 2 constraints which are coming in and an additional variable that also come in. There is another way of representing it also. There is another way by which you do not define y1 as a 0 1 variable, you define y1 as a continuous variable and add 3 constraints instead of 2. Obviously, this is a more desirable one than the other one, simply because in the other one you add 3 constraints. So, it is going to increase the size of the problem. Secondly, you also bring in a y which is not a 0 1 variable, it is a continuous variable. So, the problem loses its all 0 1 structure and it will be difficult to solve that problem using the implicit enumeration algorithm. So, we will not look at that, we would rather keep this as the way to convert a product form into a single variable. So, nonlinear problems become linear 0 1 problems by this method. Any higher power automatically becomes the same variable. only when you have product forms you will get this. When you have 3 terms appearing, you can write a corresponding. The spirit is the y1 will take a value 1 only when x2 and x3 take 1. If either of them take 0, then y1 will be forced to 0. That is the underlying assumption, which is solved by both these. So, if you have 3 terms, product term coming in a single variable, then you will have one more additional constraint that would come in, and that has to be written accordingly. So, this kind of brings us to the end of the discussion on 0-1 problems. We have just seen one algorithm. Of course, there are so many other refinements. The algorithm that we saw is a very old 1959 algorithm. So, in last 45 years you could imagine much more development in this field. Nevertheless, it gives us a feel of what implicit enumeration is and how easy it becomes, particularly to write a computer program or a code which would solve 0-1 problems. We will then move into the next important topic, which is to solve problems using for a general integer programming problem. Now, we look at how we solve a general integer programming problem. We will take a specific example and explain the IP. So, we will take this problem as a standard problem and try to solve this. Now, the first thing that we do is, in all integer programming problems, right now this is a case, this is called this is an all integer programming problem, because all the variables are integers. When some of the variables are continuous and some of them are integers, it is called a mixed integer programming problem. We will first consider the all integer example. In all these kind of problems, or in general for any integer programming problem, the first thing to do is to relax the integer restriction and try to solve it as a linear programming problem. If the linear programming optimum is integer valued for all the integer variables, then it is optimal to the IP. So, the first thing we need to do is to relax the integer assumption or restriction and solve it as a linear programming problem. So, we will create the first thing by a node which says LP optimum will be x1 star equal to 28 by 9, x2 star is equal to 133 by 45, and z is equal to 273 by 45. Now, let us assume that please remember that we know how to solve a linear programming problem. Not only that, we know how to solve it efficiently. You could use many things like your column generation if needed, or the efficient ways of inverting the matrix and then solving it. Now, this LP optimum does not have an integer value for either of the decision variables. So, we need to do something to get to this, and what we do is this. Now, let us try to pictorially depict this LP optimum. Let us say we need to plot both the constraints. So, 7x1 plus 5x2 less than or equal to 7, say if we call this as 1 and 2. So, the first constraint would have a 1 0 here, x1 equal to 1, x2 equal to 0, and then we have 0 and 7 by 5. So, I have 1 0 for the first one, and x2 is equal to 7 by 5, which is roughly which is 1.4. So, this is the first line which is here. Second one would give us x2 equal to 7 by 15 which is somewhere here, and x1 is equal to minus 7 by 12 which would be say somewhere here. So, this would be our one second, let me just check. Minus 5x2, sorry, 7x1 minus 5x2 less than or equal to 7 minus 12x1 plus 15x2 less than or equal to 7. I missed the minus. I was also realizing that this is 3 point something and something else was happening here. So, right. So, this is the value. So, this is your. So, I have not plotted it all right. I need to plot the first line again. So, let us plot. The first one is 1 comma 0 and this would be minus 1.4 which is somewhere here. First line would go like this, second line would be 7 by 15 which is somewhere here, and minus 7 by 12 . So, you get your, let us say 28 by 9 is somewhere here and 133 by 45, this should be somewhere here. You assume that it goes like this and somewhere here is the LP optimum. We will say that this is 3.1 something comma 2.45, 3s are 135, so 2 point something. So, we have x1 equal to 3.1, x2 is 273 by 45 which is like 2.95. Now, what we understand from this is this corner point solution is not optimal, that is number 1. Number 2 is we would not be interested in, for example, if I take a variable say x2 under consideration and I kind of draw a line here that represents x2 equal to 2 and there is a line here which is x2 equal to 3. I know for sure that every point here on the feasible region which is above x2 equal to 2 is not actually feasible with respect to the integer programming, because I have a restriction that x2 should be an integer value. x2 can only take a value 2 or 3 if I am in this territory. x2 could take 1 if I am in another territory, but looking at the optimum, if I basically take one variable which is x2, I could do the same interpretation for x1. If I take variable x2 which is at 2.95, I know that I am not interested in this value, it is infeasible to the IP. So, my x2 can only be, I am interested in all integer values where x2 is less than or equal to 2 or x2 is greater than or equal to 3. I am not interested in any value which is in between this. So, what I will do now is I take any one of the variables which has a non-integer or a fractional value at the optimum. In this case I might take x2, I can do the same thing with x1. Look at the value 2.95 and I create two nodes from this tree, one which says x2 less than or equal to 2 less than or equal to the lower integer value, and x2 greater than or equal to 3 which is greater than or equal to the higher integer value. Because I know that any x2 which is in between these two. For example, anything that is slightly above 2 or slightly below 3, but fractional value is not desirable because it is going to be infeasible to the integer programming problem. So, you create two branches from the original LP by adding these two constraints x2 less than or equal to 2 and x2 greater than or equal to 3 and solve two resultant linear programming problems. You should not put both the constraints into the same problem, because if you put both the constraints into the same problem, you end up creating x2 infeasible. The very fact that you have written two constraints, there is no feasible area corresponding to these two, but then you know for sure that such an area you do not want to look at because it is not feasible to the IP. So, you will create two integer programming problems, two linear programming problems at every node that you branch, one less than or equal to the lower integer value of a fractional variable and the other greater than or equal to the higher integer value of the fractional variable. In this case, you get less than or equal to 2 and greater than or equal to 3, and solve this problem all over again. Solve the original LP with the additional constraint that x2 less than or equal to 2. When you do that, you get a solution x1 equal to 17 by 7, x2 equal to 2 and z equal to 31 by 7. Which means basically we are looking at, we put this constraint, and now with this feasible region I am trying to solve the problem, and I realize that this is my corner point now. From here I have moved to this point, this is for my original P1, this is for my P2. Now, when you put x2 greater than or equal to 3 to the original set of constraints, you should not put this one also, again this has already been solved. So, you put x2 greater than or equal to 3 into the original two constraints and solve the problem, you get infeasibility here. Now, that is understandable. From the graphical region one can easily see that x2 greater than or equal to 3 results in infeasibility. So, the moment a node is infeasible, you fathom it by infeasibility. Fathoming by infeasibility we have already seen in the 0 1. So, you do not proceed further, because proceeding further would mean putting some more restriction. Already it is infeasible, so putting another restriction can never bring in feasibility. So, it will continue to be infeasible. So, you do not do that. The moment it is infeasible, you fathom it. So, you fathom, which means you do not move further from infeasibility. There is no backtracking involved in this algorithm. So, just fathom by infeasibility. Now, look at this node which is active. Now, here I have, this has an integer value, this does not have an integer value. So, what do? I branch on this. I take this one, 17 by 7 is 2 point something. So, I create two nodes, one with x1 less than or equal to 2 and the other with x1 greater than or equal to 3. So, when I put an additional restriction that x1 less than or equal to 2, so now I come back here. Now, this is where my 17 by 7 is. So, let me assume that my x1 less than or equal to 2 is somewhere here and x1 greater than or equal to 3 is somewhere here. So, less than or equal to 2 will give me another one which is somewhere here. So, when I do that, I still have, I am able to get this point which is in the feasible region. So, I get x1 equal to 2, x2 equal to 2 and z equal to 4, which is a feasible solution to the IP. It is feasible to the integer programming problem, and I update the solution. I have one integer solution which I update. Now, I do not proceed further here because I already have an integer solution. So, this is fathomed by feasibility, and the moment I get a feasible solution to a minimization, this is a maximization problem. So, I have a feasible solution to a maximization problem. Feasible solution acts as a lower bound, because my optimum to the IP can only have a value of 4 or more, because I already have a feasible solution with z equal to 4. Now I go back and do the additional one and I get infeasible here when I solve it. Remember that when I am solving for this or for this, I should add both x2 less than or equal to 2 and x1 less than or equal to 2. When I am solving here, I should add x2 less than or equal to 2 and x1 greater than or equal to 3 to these two. So there are 4 constraints now, 2 additions that have come in to this. Now this infeasibility is also indicated by the graph that it is totally out of the feasible region. So it is infeasible and it is fathomed by infeasibility. Now there are no nodes that are right now hanging, the algorithm terminates when I cannot branch. Now this is a simple branch and bound algorithm. This is a simple branch and bound algorithm to solve integer programming problems. We have taken a very small and simple example which kind of terminates in 5 nodes and gives us the optimum. Now what were we trying to do? So in all these aspects, whenever we branched from a node, we were basically trying to eliminate a certain feasible region from this feasible region. For example, when we branched on the first time when we branched, we were actually trying to leave out this much of a feasible region by putting an x2 less than or equal to 2 and an x2 greater than or equal to 3, we eliminated this portion of the feasible region. So every time you branch, you end up eliminating or leaving out a certain portion of the feasible region, and somewhere in the order in which you do it, you will end up, if the problem has, the IP has an optimum, then you will reach the optimum in a finite number of iterations, but there is no way to guarantee what is that finite number. It can be a very large number of iterations, but it does converge in a finite number of iterations. That is one. Now the idea is, whenever we branch, we kind of create either 2 horizontal lines in the graphical representation, or create 2 vertical lines, and that part of the feasible region that lies between those 2, in this case 2 horizontal lines if you branch on x2, that part of the feasible region is eliminated. You look at either this or the other. It turns out in this case that it is infeasible and so on. Next. Now another important thing is this: every branch and bound algorithm basically has 3 things. It has a branching strategy, it has a branching strategy, it has a bounding strategy, and it has a node selection strategy. These are the 3 things that are associated with any branch and bound algorithm. Now what is the branching strategy for this example? What is the bounding strategy? What is the node selection strategy? 1. Let us look at the bounding strategy, that is easy. Bounding strategy here is, you fathom by infeasibility, you fathom by feasibility, and you also realize that at every stage you are solving a linear programming problem. You are solving a maximization linear programming problem. Therefore, the LP optimum is an upper bound to the IP optimum. I have a maximization problem. For example, here the optimum was 4. Now the value here, if you divide 273 by 45, would be anything between 5 and 6. 45, 6 or 2, so 6 point something, 6 and 3 by 45, we got 6 point something here. Now that is an upper bound to the IP optimum. Now when you branch and get 31 by 7, you get 4 point something, which also acts as an upper bound. In fact, right here you could have done one more thing. Now this is 4 point something, all your coefficients are integers. So 4 point something would imply that 4 is a realistic upper bound for the integer programming problem. Here I have a feasible solution with z equal to 4, which is a lower bound. Feasible solution is a lower bound, and right here I have got it. So even if I proceed here, I can only get 4 or less, and I do not even have to evaluate this infeasibility. I can just say right here that I have found the optimum. Now those things are possible depending on certain situations. So the bounding strategy would be every node solves a linear programming problem with a maximization objective. So what we get is an upper bound. So the bounding strategy would be all these: bound by infeasibility, bound by feasibility, and the fact that every bound we solve, every node we solve a linear programming problem which gives an upper bound to the IP optimum for a maximization problem. Now what is the branching strategy? We could have, in the same problem we could have branched on x1 or x2 at any stage. We started here branching on x2. We could have started the same thing branching on x1. Sometimes branching on x1 would result in fewer nodes, sometimes branching on x2 would result in fewer nodes. So branching strategy would simply imply having chosen a node to proceed further, from that node which variable are you going to branch on. Very conventionally what you would do is you would pick a variable which has the largest fractional component and then you proceed. It is a very customary practice that you take a variable that has the largest fractional component. In this case this had 3.1 something, so the fractional portion was a 0.1. Here you had a 2.95, fractional portion is a 0.95. So it is customary to take the 1 with that. There is no proven evidence that if you branch on the variable that has the largest fractional value, you will get the optimum in fewer iterations. There is no such proven rule. It is only a greedy approach where we think that because it is very close to an integer value, you might get that value in the next one. For all you know, the x2 equal to 3 never figured in the solution. 2.95 would make it closer to 3, but the optimum did not have x2 equal to 3. In fact, x2 equal to 3 was infeasible. But it's customary that you branch on a variable that has the largest fractional component. Now what is a node selection strategy? Node selection strategy, we actually did not have any node selection strategy in this example. The reason being, you started with your first node which was a linear programming solution, and then you branched. One of the branches became infeasible and only one branch you could proceed further. So this was the only node available for selection. From here also we branched, and right here we got the optimum. So we did not have any node selection to do. By default we were having only one node in this example. Now there can be situations where we may have more than one active node. In fact, in almost all situations there will be a lot of active nodes, and you may have to choose one out of the existing active nodes to branch further. An active node is one which has not yet been fathomed, and it has a fractional value for at least one of the integer variables. That is called an active node. So normally you branch on that node that has the largest value of the upper bound. LP optimum indicating the upper bound, that node among the active nodes that has the largest value of ZLP, the LP optimum, is usually the node that is selected for branching. Again it is a greedy approach. For example, when I say here 6 point something, if I choose a node with, there is a node with an upper bound of 6 point something, there is a node with an upper bound of 5 point something, let us say. If it turns out that the LP optimum is 4, that is, it is pretty much possible that proceeding from the node with 5 point something may reach the optimum faster. But we always end up being optimistic, saying if there is a node with an LP value of 6, it gives us an outside chance of getting an IP value of 6, whereas proceeding from a node with an LP value of 5 point something can only give us at the maximum an integer programming solution with z equal to 5. So we do not do that. Eventually all nodes have to be evaluated. So there is nothing like saying that I will not do this, I only branch on one node. But by and large all these three things have to be done very meticulously, and it is also well known that depending on the choice of these three, both the memory requirement as well as the time requirement of the IP problems are defined. Why does a memory requirement come in? Here we do not, in the earlier 0 1 implicit enumeration algorithm, the variable to branch could take only 2 values. So, backtracking was a very convenient way of moving from one node to another in a branch and bound tree. A variable that takes a value 1 can only take a value 0. Here that cannot happen. For example, x2 may be between 2 and 3, so you branch on x2 with 2 and 3. Somewhere later when you move down, x2 would take a value between 1 and 2 and you might do some branching. So, you do not have that the variable appearing only once in the branching with 0 1 and so on. So, here you have to store all the active nodes. Storage becomes an issue in this kind of a branch and bound. Storage was not an issue in the implicit enumeration algorithm. So, normally right at the time of storing you sort in the decreasing order of LP optimum and then store at the right place, so that your node selection becomes easy. You always branch on the first active node, the node that has the largest LP optimum. So, these are the various issues associated with a branch and bound algorithm for integer programming. The 3 strategies: branching, bounding and node selection, as well as the branch. Every time we branch from this, we actually eliminate a certain area from the feasible region, which is bounded by 2 horizontal lines or 2 vertical lines. Now, if we have, this is for an all integer problem where all the variables are integers. If we have a mixed integer programming problem where some of the variables are continuous and some of the variables are integers, this becomes a little easier, because out of all the variable set there are only going to be fewer variables that have to be integer valued. So, in some sense with fewer nodes we should be able to terminate at the optimum. You do not have to branch on the variables that have greater than or equal to. You need to branch only on those variables that have integer restrictions and at that point do not have integer values. So, this is how the general branch and bound algorithm works with the 3 things: branching, bounding and node selection. Now, we look at another way to solve integer programming problems. In fact, before that we need to look at one more aspect, which is this. If you take this branch and bound tree, for example, we should remember that when we created an additional node from here with the addition of a constraint x2 less than or equal to 2, one need not solve the linear programming problem all over again. One could use sensitivity analysis as an additional constraint and do it, or one could simply do an upper bounded simplex from the existing LP optimum. One can easily do that. You have 2 constraints, because all these constraints are only bounds, you have 2 constraints, you will continue to have 2 constraints. Even if you do sensitivity analysis, you will be introducing a 3rd constraint explicitly. Whereas, when you straight away plug in an upper bounded simplex from the existing optimum basis, you still retain the 2 constraint thing. The bound goes out of the problem. So, typically the problem size, the number of nodes may increase significantly, but the problem size is always a 2 constraint. There could be some other issues when you start doing it, but certainly the problem the constraint set does not become large because of the addition of these, and each one is only a kind of a bound. But in spite of that, the problem is a worst case hard or enumerative kind of an algorithm, because you do not know how many nodes you will evaluate before you terminate. So, let us look at another way to solve integer programming problems. As usual, we solve this first by the simplex algorithm to get an LP optimum. So, let us construct the simplex table and then solve it first using the simplex algorithm. So, you will have x1, x2 x3, x4. We start with x3 and x4 here. So, you would have x3, x4 here. You will have 1, 1, 0, 0, 0, 0, 7, minus 5, 1, 0, 7, minus 12, 15, 0, 1, 7, 1, 1, 0, 0. So, you could enter on x1, you could enter on x2. So, let us go back and enter on the enter x1 here. Find that there is only one leaving variable. So, this is the leaving variable. Because of this negative, there is only one leaving variable. So, I have x1, x4. So, I have 1 and 0. 1 minus 5 by 7, 1 by 7, 0, 1. This plus 12 times this, so 0. 15 minus 60 by 7 is 45 by 7. This plus 12 times this is 12 by 7, 1. 7 plus 12 into 1 is 19. So, we get a 1 here. So, this becomes 0, this becomes 0. 1 plus 5 by 7 is 12 by 7, and this is minus 1 by 7. So, x2 enters again. There is only one leaving variable here, which is here. So, I have x1, x2, 1, 1. This is the pivot element. 45 by 7 is the pivot. So, multiply or divide by the pivot to get 0, 1, 12 by 45, 7 by 45, 19 into 7 is 63, 133 by 45 here. This plus 5 by 7 times this 1, 0. 1 by 7 plus 5 by 7 into 12 by 45. 12 by 45 is 4 by 15. So, you get 1 by 7 plus 12 by 7 into this 12 by 35. So, 1 by 7 plus 12 by 35 is 17 by 35, and you get something else here, minus 5 by 7, 1 by 7, 0, 12 by 7. So, this should become 12 by 45, which is 4 by 15, just written down this 4 by 15, and you have a 7 by 45 here. This is 1 by 7 plus 5 by 7 into this. So, 20 by 105, which is 4 by 21, 4 by 21. So, 1 by 7 plus 4 by 21 is 1 by 3, it is 1 by 3. So, this plus 5 by 7 into this, which gives me 5 by 45, which is 1 by 9. So, this plus 5 by 7 into this. So, 1 plus 5 by 7 into 133 by 45. So, that is 28 by 9, which we know anyway. So, 28 by 9. So, the z value is 28 by 9 plus 133, 273 by 45, and you get 0, 0, minus 9 by 15 minus 4 by 15. So, this is the LP optimum that we have. Now, we realize that both x1 and x2 are not integer valued. We can choose any one of them and proceed further, and we just now saw that it is customary to take that variable which has the maximum fractional portion for subsequent addition or move in the algorithm. So, we take this and now we write this in the form of an equation, and this would become x2 plus 4 by 15 x3 plus 7 by 45 x4 equals 133 by 45. Now, because this is a simplex iteration and it represents LP optimum, this will have to be non-negative. Even if it is a dual simplex iteration, it does not matter, because this represents an LP optimum, this has to be non-negative. What we do is, we rewrite this in such a way that I do not have a fraction for x2, so I just write x2. The fraction, the coefficient of x3 turns out to be a fraction less than 1, right, 4 by 15. So, I just write it as 4 by 15 x3. For example, if this coefficient had been 19 by 15, I will write it as plus 1 x3 plus 4 by 15. I will always write it as an integer plus a positive fraction, which means if it were minus 4 by 15, I would have written it as minus 1 plus 11 by 15. I should always write it as an integer plus a positive fraction. So, this becomes 7 by 45 x4 becomes 2 plus 43 by 45. So, right hand side is also written as an integer plus a positive fraction. Now, we use this and try to create a cut, which we will see in the next class.